Hello everyone. We are basically at the end of chapter 5 and we are going to talk about energy analysis of unsteady flow processes. So we already talked about different steady flow processes such as turbines, the flow in turbines, the flow in nozzles, diffusers, and so on and so forth. Today we want to talk about basically unsteady flow processes. So if you remember, the definition of a steady flow process was such that we had changes within our control volume. We didn't have any changes within our control volume, and that was basically how the steady flow process was. Now if you look at the right picture here in this slide, you can see that in unsteady processes, usually we have a mass coming in and the total mass change and energy change within our system does not stay constant. So basically the right hand side of the energy balance equation or the mass balance equation is not zero for unsteady flow processes because we have energy change within our control volume with time. So time is a factor basically that changes, that affects the way we write the equations. So you can see two examples of this on the right side, and one example, the top one, is basically a control volume. There is a valve and there is a supply line. If you open the valve, the gas or whatever or fluid basically which is inside that supply line will enter your control volume, and the mass of your control volume will change with time. Also there is a flow energy coming into your control volume, right? So the added to your total energy, so your total energy within the control volume is also changing with time. So that's basically an unsteady flow process, and we want to talk about how would the Peirce law of thermodynamics look like for this type of process. So if you look at basically the equations here, the mass balance equation, we have mass in minus mass out equal to total mass change in our system. And in this, because this is an unsteady flow process, then this is not zero, and this is the definition. So final mass in our system minus initial mass in our system. So the mass in minus mass out, which is shown with ME, escaped mass basically, is equal to the total change in the mass of our control volume within that period of time that we did the process. Okay, so M2 is the final mass of our system, M1 is the initial mass of our control volume, Mi is the basically how much mass is entering, M in basically how much mass is entering our control volume, and Me is how much mass have left our control volume for that period of time that we had this process. Now once we stop the process and we close the valves of our system, there is no mass coming in, mass going out. We are actually dealing with a closed system right after the process has finished. So that's a closed system at the end of our process. However, when the process is going on within that time that the system is open, there is a mass coming in. That is basically an unsteady flow process. So how does the equation look like? So the energy balance is the energy difference coming, energy in minus energy out, is the delta E system. Now the left hand side of the equation is the same as open systems. So the energy in minus energy out is defined by this equation. You can see it's exactly the same as open systems, no difference. Q in plus W in plus sigma m theta. What is theta? Theta was the enthalpy plus kinetic energy plus potential energy. And this is sigma in. It means that the mass which is coming in, these are the properties of the mass entering your system. And minus Q out if you have any heat leaving your system, and work out again if your system is doing some work to its surrounding. And sigma m theta out, that's basically again enthalpy plus kinetic energy plus potential energy of the fluid that is leaving your system. So that's the left hand side. The right hand side of the equation is not zero for unsteady flow process. For the steady flow processes, this was zero, right? So zero for steady flow, for unsteady flow, this is the definition, right? So you can see the definition is M2E2 minus M1E1, correct? So so we have this, right? And we define basically this. So what is E then here? E is basically internal energy plus kinetic energy plus potential energy. So please notice this is U on the right hand side of your equation. This is not theta, right? Why? Because at the end of the process and at the beginning of your process, your system is still closed. So you consider it as to be basically a closed system initially and at the end of the process, right? So for a closed system, you don't have enthalpy. What you have is basically internal energy plus kinetic energy plus potential energy. So that's why you see on the right hand side of the equation, you use basically energy, E, right? As opposed to theta that you see, right? So theta is not used on the right hand side of the equation. This is the most important part you need to be careful about. Okay, so that's basically how you write the equation. In the next video, we will talk about we do an examples of this basically process. Okay, here you can see some examples again. You have some stream and then you open the valve. Initially your system is closed, then you open your system, the mass coming in, fill your system, then again you close the valve. So at the beginning of your process and at the end of your process, your system is a closed system, but within the process, the time frame that this process is happening, the steam is coming into your system, then that is an open system. So the left hand side of the equation, you have to use the theta. On the right hand side of the equation, you have to use the energy of the system, which basically is written based on the internal energy. Okay, so in the next video we'll do an example and see you momentarily.